From the Lagrange function, we can immediately deduce a number of conservation laws. First of all, we notice that the Lagrange function does not depend explicitly on time. This implies that the Hamilton function is a constant of the motion. The kind of coordinate transformation that we have done to go from Cartesian coordinates to generalized coordinates, that was a time-independent coordinate transformation. And the kinetic energy is quadratic in the velocities, in the generalized velocities. So all the prerequisites are in place so that we can identify the Hamilton function with the total mechanical energy. So in our case, the Hamilton function, which generally has this form, pi qi dot minus Lagrange function. In our case, this is just the total mechanical energy, and that is the rotational energy. We don't have any translational part in the kinetic energy, plus the potential energy. And this is a constant which we call E. It's the total energy of the system. Then we already noticed that two of the three Euler angles are cyclic coordinates. The Lagrange function does not depend on the Euler angle psi, and it does not depend on the Euler angle phi. Let's start with psi. Doesn't depend on psi. This is cyclic, and therefore the associated generalized momentum, p psi, is a constant of the motion. What is p psi? Physically, it's the generalized momentum associated with or conjugate to the Euler angle psi. Remember the Euler angle psi? That was an angle in the E1 primed, E2 primed plane. Maybe we can have a quick look at the definition of the Euler angles. Here you see the angle psi, this red angle. That's the angle between EK, the green vector, and E1 primed, one of the blue vectors. And it's an angle in the plane spanned by the basis vectors E1 primed and E2 primed. And this plane is perpendicular to the axis E3 primed, to the basis vector E3 primed. So psi denotes a rotation around the E3 primed axis. Now remember from the definition of the angular momentum and also from our consideration of symmetries that the momentum associated with an angle is the angular momentum component with respect to the rotation axis. So here in this case, we rotate, when we vary the angle psi, we rotate around E3 primed, and therefore the associated generalized momentum, p psi, is the angular momentum component L3 primed. Yeah, it's the L3 component in the body fixed frame, in the primed basis. So p psi is nothing but the component, the third component of angular momentum in the primed basis. You calculate this generalized momentum by taking the partial derivative of the Lagrange function with respect to the velocity psi dot, the generalized velocity psi dot. And when you insert the Lagrange function that we had obtained and you do this partial differentiation, you find this equals theta 3, that's the third eigenvalue of the moment of inertia, times psi dot plus phi dot cosine theta. So this quantity is a constant of the motion. Then we observed that also phi is cyclic, and therefore the generalized momentum associated with phi is also a constant of the motion. Now phi is of rotation, or the angle phi characterizes a rotation around the E3 axis in the inertial frame. Again, let's have a quick look at the Euler angles. You see the angle phi down there. That's the angle between the black basis vector E1 and the green vector EK. E1 and EK lie in the plane spanned by the basis vectors E1 and E2 of the inertial frame. And this plane is perpendicular to E3. So the angle phi characterizes a rotation around basis vector E3. And therefore the generalized momentum associated with the angle phi is again an angular momentum component. And this time it's the component L3. It's the third component of angular momentum in the inertial frame. So this physically is the angular momentum component L3. You obtain it by deriving the Lagrangian with respect to phi dot, and the result is theta 1, that's the first eigenvalue of the moment of inertia, times phi dot sine squared theta plus theta 3, third eigenvalue, then psi dot plus phi dot cosine theta times cosine theta. Here you observe that this part here is identical to that one here. So in fact, what I encircled in blue, you can replace by p psi, which is also a constant of the motion. So the two constants of the motion associated with the cyclic coordinates are p psi and p phi, and in the expression for p phi enters also p psi. When we look at this last equation for p phi, then we have on the right hand side, we have eigenvalues theta 1, theta 3, which are constant in time. Theta 3 actually is absorbed in the definition of p psi, and p psi is constant in time. And then we have phi dot and theta. And we can solve this for phi dot. We can write phi dot as p phi minus p psi cosine of theta. And let me write explicitly that theta is time dependent. The angle theta, the Euler angle theta, varies in time. Divided by eigenvalue theta 1 sine squared Euler angle theta, which is a function of time. Obviously, this makes the left-hand side a function of time as well. And let me give this equation another number. That's equation number 4. This tells you that if you knew the Euler angle theta as a function of time, if you knew that, then you could insert this in the right-hand side. P phi, p psi, and the eigenvalues theta 1 are all constants of the motion. So if you knew all that, then you would have an equation, a first-order differential equation for phi, and you could solve for phi. And you would obtain phi as a function of time. Just for completeness, let me just note here that these are all constants. What does that describe, this equation for phi? Remember once again the meaning of the angle phi in this graph here. It tells you how the green vector EK, how that rotates around E3. It also tells you how, in the same vein, it tells you how E3 primed rotates around E3. So it tells you how the figure axis, which is spanned by E3 primed, how that rotates around E3. Therefore, this equation here characterizes or describes the rotation, which is called the precession, in the same terminology as for a free symmetric top. That was the precession motion. It describes the precession of E3 primed and hence the figure axis around E3. Now the precession happens with a certain angular velocity, and that angular velocity is precisely the phi dot that we have there. So this is with angular velocity. And here already note an important difference to the free symmetric top. In the case of the free symmetric top, the figure axis rotates, precesses around E3, which coincides with the angular momentum axis. We chose the inertial frame in the case of the free symmetric top. We chose the inertial frame such that the axis spanned by E3 coincides with the angular momentum axis, which is a constant in time, constant of the motion. So in the case of the free symmetric top, the figure axis precesses around this axis with a constant angular velocity. Here you see that on the right-hand side, the expression for phi dot is generally a function of time, because phi dot, the angular velocity of precession, depends on the Euler angle theta, and theta in turn is a function of time. Yeah? So, important difference here, the heavy symmetric top precesses, but the angular velocity of precession varies in time. Now we can go one step further, and we can use this last formula, number 4, as well as the expression number 2, the formula for p psi, and combine it with energy conservation, so equation number 1. In there we have rotational energy plus potential energy is equal to E, this constant total energy. We have to use the expression that we found for the rotational energy. That is on the previous page when you look at the Lagrangian inside the box. That's on the right-hand side, the terms on the first line. Yeah? On the second line you have the potential energy, that's minus mgs cosine theta. And on the first line you have the rotational energy. In there you have phi dot and psi dot. And what you can do is that you can insert for phi dot, you can use the formula that we had found for phi dot, formula number 4. And psi dot, in fact psi dot plus phi dot cosine theta, you can replace by the generalized momentum p psi up to an eigenvalue of the moment of inertia. So you can eliminate from the right hand side, you can eliminate phi dot and psi dot and instead write the right hand side as a function of the associated momenta. So what we do is that from these 4 equations that we had on the previous page, we insert equation number 2 and equation number 4. We use these 2 equations to replace in the expression for the total mechanical energy, in particular in the expression for the rotational energy, to replace phi dot and psi dot by the generalized momenta p phi and p psi. So we use equations 2 and 4 in equation number 1, which was the equation for the total mechanical energy, which is the constant E. Then we find the total energy is theta 1 over 2, so first eigenvalue of the moment of inertia, times theta dot squared, plus, then we have, where previously we had the phi dot, we can replace that by an expression where we have the momentum p phi minus generalized momentum p psi cosine theta squared divided by 2 times eigenvalue theta 1 sine squared theta. Then we have p psi, the generalized momentum p psi squared, divided by 2 times eigenvalue theta 3 of the moment of inertia. And then we have the potential energy, which is still mgs cosine theta. And all of this is a constant of the motion. You see, the total mechanical energy has now become a function of theta dot and theta only. Everything else that features in this expression for E are constants of the motion. The eigenvalues theta 1, theta 3, the generalized momenta p phi, p psi, these are all constants of the motion. And the only variable that you still have that may depend on time is the Euler angle theta and its derivative theta dot. These last 3 terms here, we can view that as an effective potential that is a function of theta. And now this looks just like the total energy of a one-dimensional mechanical system. We have the kinetic energy, theta 1 over 2 theta dot squared. That's like mass over 2 velocity squared in one dimension, plus some potential which depends only on position, and in this case position is the Euler angle theta. So we have effectively reduced everything to a one-dimensional problem. We can consider this graphically. We can draw the effective potential as a function of theta. The Euler angle theta takes values between 0 and pi. When the angle theta is close to 0, then you see in the expression above for the effective potential, you have in there, in the first term, you have 1 over sine squared theta. When theta goes to 0, the sine goes to 0, and therefore the denominator goes to 0, and that term explodes. So for very small angles, the effective potential becomes very large. Yeah? In here, this is dominated by 1 over sine squared theta, which for small angles goes like 1 over theta squared. So for small angles, it explodes. When you approach pi, you have the same phenomena, because the sine of pi is also 0, and therefore the potential will also explode close to pi. You can try to plot this function, and qualitatively it will have a shape like this. It has a minimum somewhere, and then it diverges as it approaches the edges of its domain. When you have a fixed total mechanical energy, E, somewhere here, which is a given constant of the motion, then you recognize immediately, and you remember our discussion of one-dimensional problems at the beginning of the semester, that there are 2 turning points. There is a minimum angle, and there is a maximum angle, and in between, the system will perform bounded motion. At any angle in between this range, say here, then this difference here, this is just the kinetic energy at that point. So that's theta 1 over 2 theta dot squared. Yeah? So at the turning points, the kinetic energy vanishes. Theta dot is 0, and then the system turns around and goes to the other side. So you see qualitatively that you have bounded periodic motion, so that's theta of t. Bounded will exhibit bounded periodic motion between theta min and theta max. And this oscillating movement between a minimal and a maximal angle theta, that is known as nutation. As I mentioned before, if you try, it's not possible to calculate the function theta of t analytically. It's a rather complicated integral that you would have to solve. You can do that numerically. But here we shall be satisfied with understanding the qualitative behavior of the system. So let me try to sketch this, or to summarize our findings in a few sketches. Let me draw a sphere. Here is the axis E3. Here is the figure axis spanned by E3 primed. The angle between these 2 axes, this angle is theta. Now the 2 circles that are indicated here on the sphere, let these correspond to theta min and theta max. So at any time t, the angle theta will be somewhere between this theta min and theta max. Now the figure axis rotates around the axis E3 with angular velocity phi dot. And let me try to indicate here the angle phi. That's the rotation of the figure axis around E3. So what will the motion look like? We have a superposition of two oscillating movements. We have the precession of the figure axis around E3, and at the same time the angle theta varies between theta min and theta max. So the trajectory will somehow look like this. It's a superposition of two types of motion. One is the rotation around E3, which would be the precession of E3 primed, i.e. the figure axis around E3. And the second type of motion is the nutation that's going back and forth between theta min and theta max. That's the nutation. The green trajectory is a combination of precession, which is the motion around the E3 axis, and nutation, which is this wobbling back and forth between theta min and theta max. Depending on the values of your parameters, the motion can also take slightly different forms. I mean, it's always this superposition of these two types of motion, but depending sort of on the relative speeds of these two motions and amplitudes of these oscillations, it can also look like that. Or it can look like that. That would be a rather special motion. Or it can be the type that I drew up on the sphere. So two key differences to the symmetric, to the free symmetric top. One I already noted, that the speed of precession, the angular velocity of precession is not constant in time, it varies in time. And the second difference, of course, is this nutation movement, which you don't have for a free symmetric top. This angle theta varies in time and it oscillates between a min and a max value. Let me finally show you a little animation video. It's a gyroscope. The precession movement that you see, and now there's an additional weight. precession and nutation.